Okay, last time we discussed types of liquid chromatography, part 2. But what did we have there in this part 2? Yes, politically correct answer, other types of liquid chromatography. More specifically, please. Normal phase chromatography. Aha, helic I heard, and ion pair chromatography. That's correct. Slide number 5 started helic, hydrophilic interaction chromatography. And then also we had this ion chromatography. So what did you remember about hydrophilic interaction chromatography? Just issues. What about solutions?
Very useful for very polar compounds.
Okay. Yes, and that's its main use or main niche of its use. Okay, and then but how is this achieved? This type of chromatography.
Water layer on top of the solid carrier.
Okay, how can we get water layer on top of this solid carrier?
Different phase mostly consists of water with something else, and
Okay. Yes, stationary phase is water layer, but how do we get to this water layer on this solid carrier? So if we just put water there, then it will be washed away, isn't it? So how to guarantee that it stays there or remains there?
all the things made out of water and acetonitrile.
Exactly. So the mobile phase contains both water and acetonitrile, and this stationary phase layer, this water in the stationary phase layer is renewed constantly. So from the eluent, new molecules of water emerge. They go in the stationary phase. I didn't say the word in which mechanism. So, okay, the new molecules of water stay there, and the old ones are washed out of the column. So this equilibrium is dynamic. Okay, but what is the process how to attach water molecules to remain stationary? Sorry? Adhesion. Well, we used a different word.
Polar interactions.
Polar interactions, yes. So we use polar or non-polar stationary phase, the carrier. Polar, yes. And most typical one is what kind of carrier? Silica, yes, just bare silica. Sometimes also ionic groups are attached to the silica surface, but just bare silica is the most common one. And we already discussed the mobile phase, typically acetonitrile mixed with some water. And what is the strong eluent component? Water, yes. Increasing the concentration of water or the percentage of water in this mixture makes the analytes elute faster. So yes, water is the strong component. All right, and then let's jump to ion exchange chromatography or ion chromatography. Any highlights from this topic? What for is it useful? Mm-hmm.
It's used for ion cations or anions.
Okay. Yes.
In case of cations, we use different places with negative charge. And also
Mm-hmm. That's right. And what is the typical element in this type of chromatography?
like acids
Acid or
base and buffer.
what was the other one?
Using some buffer.
Yes, acidic buffer, basic buffers, or acid solutions or base solutions. So yes, both are used. Depending on whether anions or cations are analyzed. Okay, so let's then rapidly go over ion exchange or ion chromatography. We use them as synonyms in this course. Then there can be also counter ions. We will see those a bit later once again. And ion exchange equilibria takes place at the stationary phase. Then if the ion exchange group, in this case it's carboxylic acid, and its cation exchange group, then if this behaves as a weak acid, then full set of equilibria is possible. So this weak acid may be protonated, deprotonated. It may be in the form of so-called sodium form, as it's often called technically. Then the analyte may partition to the surface, and the analyte may also be deprotonated, in this case, to become neutral, and this neutral form doesn't interact with the stationary phase. So the full set of interactions. And we see that in several of those processes, protons are involved, which once again shows how important acid-base equilibria is in chromatography. We also discussed why to use ion chromatography and how it can be incorporated and, for example, preparative chromatography or multidimensional chromatography. So it has its uses. And this is where we stopped. We didn't specify what kind of stationary phases, stationary phase materials are used. In principle, silica can be used as stationary phase, but as silica has very limited stability, especially with respect bases. Usually silica starts to dissolve already at pH 7 or 8, so that we can't use it in basic solutions at all. So therefore, silica is not very often used. Instead, organic polymers are used as stationary phase carriers. And cross-linked polystyrene copolymer is the most common one. So polystyrene structure or fragment is shown here. So no wonders here. In principle, also some hydrous oxides can be used, alumina, zirconia. So those are respective oxides then. Those act as cation exchanger at high pH and anion exchanger at low pH. So interesting properties. But still, mostly the polymeric ones are used. Now, The copolymers of styrene and divinylbenzene is the most common one, and the surface of those particles is functionalized. So with it can be functionalized for cation exchange or anion exchange. And the good side of using those organic polymers is that it is highly pH tolerant. So from pH 0 to pH 13 can be used. So we can analyze full range of acids and bases and cations and anions, therefore. And this gives us a lot of freedom. But it also has a disadvantage, and those particles are soft. So soft means that if we would try to use high pressures, as is quite common in high performance liquid chromatography, where we use high pressures, then with those organic polymers, this is not possible. Just the particles are deformed and the pressure in the column increases even further. So it's easy to ruin the column. So the efficiency is limited by this softness of the particles. We cannot prepare very small particle sizes because then the column would cause high back pressure, and back pressure is not possible. High back pressure. Therefore, bigger stationary phase particles are used, which are less efficient in separation. So, column length and flow rate are limited, and we have to strictly follow those limitations, otherwise we may damage the column permanently. So analytes most often are acids or bases, and of course the stationary phase and analyte ion should be oppositely charged. Can it be otherwise, that we use stationary phase which has negative charges on it to analyze anions? Interesting question, right? Well, perhaps not topic of this course, but it can be done, and it is done occasionally. And the trick here is to use some divalent metallic cations. For example, calcium cations, they partition to the negatively charged stationary phase, but still their one positive charge is let's say free, and then analyte can interact with this positive charge. So yes, occasionally this way of chromatography is used, but not very common. Anyway, let's stick to this normal case where we use anion exchange columns for anions and cation exchange columns for cations. All right. Now, how does the retention depend on eluent pH if the analyte is strong acid? So let's take this question first. The analyte is strong acid. So how does the pH of eluent affect the retention?
To have the acid deprotonated and then interact better with the substrate.
But we are speaking about strong acids. So
It would be convenient to have a basic pH in order to have it deprotonated and then be easier to interact with the stationary phase.
So you mean that eluent affects the protonation, deprotonation of analyte?
Yeah. It would be convenient to have the analyte to deprotonate in order to, as it is a strong acid, it would be super easy to deprotonate it, deprotonated, and then interact with the.
Okay, yes, okay, yes.
I think my opinion would be we need, in a strong acid case, we need the resin, the groups and the resin to be negative charge. So
Yeah.
we'll,
Negatively charged.
yeah. So no, if it's organic acid, so it's counter ion will be positive charge. No.
Counter ion.
Negative, no. So
Acid. Some kind of, let's say, strong acid, let's say sulfonic acid. So this is our analyte.
yeah.
Okay. So it's anionic. What kind of stationary phase should be used? Positively charged. Yes. Okay.
So we need to make the group and the resin positively charged. So the pH of the medium should be less than the pH of the group and the resin to make it.
Make it to protonate this group. Okay. Others, do you agree? Okay, first of all, let's start from the analyte itself. If it's said that it's strong acid, then it means that it's deprotonated at all reasonable pH values. So eluent does not affect its protonation, deprotonation, it's just deprotonated. So this is what the strong acid means. Now, concerning stationary phase, we didn't say anything about the stationary phase. We just know that it should be able to interact with analyte, so yes, positively charged. But whether it's strong or weak, we haven't discussed this.
We did
Yeah, earlier, yes.
Yeah.
Yes, we did, but not here at this slide. You see, this is the next point in this list. So we can discuss both cases, that the resin is anionic change resin and of the strong type. Let's start with the strong type. Strong type means that this resin is positively charged at all pH values. Okay. And now let's consider the influence of eluent pH in this case.
So it will be always positive in the resin?
Resin is always positively charged and acid is always negatively charged.
Maybe it will interact with the counter ion in some way, like the counter ion that will be replaced by the analyte will have some effect.
if the analyte itself in the beginning was, for example, in the form of sodium salt, then does this interact with the stationary phase? No?
I have an idea, but I'm not sure. Like, if it's like the pH is low, so maybe the analyte will be more into the mobile phase because it has like a lot of positive charge around it, so it doesn't need to go into stationary phase.
But why positive charge around it
Low pH.
at low pH? You mean that in acidic environment it has
Surrounded by
positive? But why don't you have yes?
The counter ion will not have, like the negative counter ion that may be interacting in the beginning with the stationary phase will have like some impact if the or some result if the eluent in the pH of the eluent is different.
Yes.
Maybe, for example, chloride ion.
Sure. If the eluent contains, for example, hydrochloric acid, then chloride ions are present and they compete for the stationary phase surface with the analyte. That's true. Oh yes, this ion would compete there, and this is the case. But in general, pH directly itself is not involved much in this equilibrium, not directly. It's the acid anion. So instead of this, we could also add just salt, which has chloride ion, and this competes as well. So if both are strong, then we can expect strong interaction between them because there aren't so many factors which can force the analyte out of the stationary phase, back into the mobile phase. Yes?
If you have acidic environment and the anion is also competing with the so in this case the retention time will be low, right?
Yes. The more chloride ions are present, the shorter will be the retention time of the analyte. Yeah. Okay. Now we could go over all the cases. Oh, I didn't have camera on. Sorry, now the figure is already drawn here. So there are 4 cases. Strong acid with a weak and strong resin, or weak acid with weak and strong resin, and plus then bases also. But they all are quite symmetrical, I would say. Acid, base, positively, negatively, all comes the same. Right? Or do you mean that we need to discuss all those cases? No, not you. We here, I mean. Do you want me to explain or that we all discuss all those cases? There will be many because 4 for acids and 4 for bases. 8 different situations.
We can discuss one case like the
okay.
hydrogen side one. Like how the pH.
Okay, so you mean that we take some, let's say, weak base? Okay, yes.
In slide 15, like same group can be used, and depending on the pH, like it can be used as ion.
16.
Yeah, this one, hydrogen side.
Well, I'm not quite familiar, I have to say, with this trick. So how the pH? Okay, I will check it out and refer to some material in Moodle then. Because yes, they are used, but the mechanisms I'm not very familiar. Okay, but I mean here, shall we go over? No? Yes? If there is silence, then we won't. Okay, in principle, all the necessary equilibria are covered here. So this is the most complicated case where all the groups are so-called weak type. So they can be protonated and deprotonated. Therefore, their presence or the presence of charge is affected by the pH of the eluent. So now we just have to consider that in principle, this analyte can be of strong type, so it's always charged. Therefore, this equilibrium number 1 is non-existent. This is one possibility. Another is, which is very common, that the stationary phase is of strong type, so it cannot be protonated. Therefore, the equilibrium number 3 does not exist. So we have always negatively charged, and that's it. So I suggest that you think it over, and if you have doubts or questions, then please ask next time. Yes?
We have only discussed what makes the stationary phase and usually strong. Like in the blackboard example, and in this case, it's strong.
Yes.
But what if it's
in this example, it's weak. Over here, it's weak.
okay?
This carboxylic acid is a weak acid, and therefore, if the eluent is acidic, its pH is lower than the pKa value of this group, then it's protonated and it loses its capacity to bind cations. Okay. Now this weak acids and retention factor. Oh, the retention factor of weak acids depends on pH of eluent. We could have guessed, right? So if the pH is high, the acid is deprotonated, and then it interacts, has more interaction with stationary phase, therefore the retention factor is higher. All right. Yeah, and then there is a question for think about why can't we analyze acids or bases always by reverse phase chromatography? Because in principle, if we look here, then we could lower the pH to the extent that the acid is protonated. And then in reversed phase column, the retention time would be long. It's about reversed phase. So why don't we do this always?
Like too much acid, or like put so much in to keep the pH low.
And sometimes even too much is not enough. So in case of strong acids, they are always deprotonated. So no matter how acidic the environment is, if it's still water solution, then strong acids will be dissociated. And yes, the silica gel does not resist that that acidic environment, and starts losing the modifier groups, these C18 groups. Those will be hydrolyzed from the particles. All right, now back to ion exchange chromatography. Here is one example of cation separation. And I would make it a bit larger. Oh. So we see that lithium elutes first, then sodium, then ammonium, potassium, rubidium, cesium, then come doubly charged ones, strontium, magnesium, calcium, strontium, barium. So it makes sense that singly charged ions elute first. We can expect that they have less interaction with negatively charged surface, and then come doubly charged, and then somewhere triply charged, and so on. But why do singly charged ions separate from each other? Wouldn't sodium and potassium, or lithium and sodium, have equal interaction? Size? So how does size affect this interaction? Yes, the smaller is the size of the ion, the stronger is the interaction. But lithium is definitely the smallest. And for some reason it elutes first, so the interaction seems to be the weakest. And molecular mass is the smallest, yes.
So the lowest molecular mass, the faster elution, or the resistance effect.
Why? Okay, let's not torture you. The answer is on the next slide. The answer is solvatation. What matters is the solvated radius of ions. And it appears that lithium ion is the smallest, but in the smallest ion, the power of coordinating water molecules around it is the strongest. So it arranges water molecules around it, making the solvated radius the biggest. So lithium has the biggest solvated radius. Sodium has smaller, then rubidium, cesium, potassium somewhere in between, and so on. So yes, you are correct that it's about radius, but radius with solvatation sphere.
The smaller the size of the element, the greater will be the solvated radius, right?
Yes, yes.
It's a rule of thumb.
Sorry?
It's like a rule.
Yes, yes. Of course, we have to compare the same charge state. Yes, singly charged, among singly charged ion, it is the rule. Among doubly charged, again, this is the rule. And if we see, then yes, within doubly charged ions, the same pattern takes place. That magnesium ion itself would be smaller, but with solvated ion, then it's bigger, and so on. Okay, and this effective radius also applies to anion exchange chromatography. So, of course, it's a bit more difficult to evaluate the size of those solvated ions here, but we can more or less guess that this is like this. So the retention order is shown also here.
But is it so that the bigger the solidation radius, the less the ion can interact with the stationary phase?
Yes,
Okay.
exactly. Yes, that's right. If small ion could approach the stationary phase without solvatation sphere, then the interaction would be strong. But as the solvent molecules are in between, then the interaction is from far away and the interaction is weak. All right. Weak and strong ion exchange resins, cation exchange. The very often used abbreviations are WCX and SCX, W weak cation exchange and strong cation exchange. For anions, W for weak anion exchange, strong anion exchange. So quite straightforward. And strong ion exchange resins are applicable from pH 2 to 12, so quite wide range. They tend to lose charge at some point, so we cannot go quite to pH 0 or pH 14. And so somewhere still the charge is lost. And weak resins. In weak resins, it depends on the pKa value of those groups. And weak ion exchange resins are common for solid phase extraction, so for sample preparation. But for analytical columns, those weak ion exchange resins are seldom used. So mostly strong type of ion exchange resins are used for analytical ion chromatographic purposes. So still, if necessary to modify selectivity or decrease selectivity just to get the retention times shorter so that we could analyze compounds faster, then the weak ones may also be used. Now, strong cation exchanger works in a very wide pH range, and more or less the capacity to exchange cations remains relatively constant from pH around 3 to 13. Strong anion exchanger in the range as shown here. And weak ones, as expected, they lose their ability to exchange cations at pH value, which corresponds to their pKa value. So here the 50% of the cation exchange capacity is lost because as the stationary phase is protonated. Okay, or deprotonated in case of anion exchange. It's wonderful how much we can do with just acid-base chemistry. Just listen this one lecture a long time ago very carefully, and everything is simple here. Okay, silica-based columns can be used just in the pH range from approximately 1 to 8. And this is the problem with silica columns, as already mentioned. And those strong cation exchange columns and strong anion exchange columns, they may catalyze some of the reactions. So, for example, ester hydrolysis may be faster in presence of those stationary phases. So one has to consider also the possibility that some reactions start taking place or take place faster in presence of a stationary phase. Okay, now about the effect of salts on retention. So far we discussed mostly the pH effect, how the hydrogen ion affects the retention. Now the other ion can also affect the retention. So counter ions compete with the analyte for the stationary phase surface, but their ability to displace analyte ions from the stationary phase is different. So there are stronger and weaker counter ions. So strong counter ions decrease the analyte retention time quite abruptly. Even low concentration of strong counter ion causes the analyte to elute fast. And weak counter ion, well, we need higher concentration of weak counter ion to make the analyte elute faster. For anions, fluoride is weak in something. Can you imagine? Usually fluoride is strong in every aspect, but now it's weak. And we see that it's weaker than chloride ion or bromide ion. But what is the reason? Try to rationalize why in this order. Yes, it's again about the solvatation radius. So fluoride ion is really small. The negative charge is concentrated into a small space, so it coordinates water molecules around it, and therefore the solvated radius is large. And as such, it interacts weakly, relatively weakly, with positively charged stationary phase. Bromide, in the contrary, the ion itself has bigger radius. The solvatation sphere is thinner, and therefore it interacts more strongly with the stationary phase and competes more efficiently with the analyte molecule. With cations, the same story. So lithium is weak exactly for the same reasons. All right, so we discussed that in ion chromatography, eluent is mostly water-based, but can we add organic solvents there? In principle, yes. Usually organic solvents decrease the retention. Methanol and acetonitrile can be used. They alter the selectivity, so we can get different selectivity when we use those organic modifiers. But again, there is a drawback. The polymeric stationary phases, polymers tend to swell because of organic solvents. Swelling, yeah, go bigger. They dissolve a bit of this organic solvent, and stationary phase particles they swell bigger. Okay, so only very low concentrations are used, and yeah, carefully. Not too high and not too big variations, monitoring the pressure in the column and so on. Instrumentation is straightforward. we have eluent, we have pump, then is the column. Of course, there has to be a sample introduction port in between. So we introduce the sample into the mobile phase flow. And then comes the suppressor. What this suppressor does, we will see it very soon. And after suppressor comes the detector. Detector is most often conductivity based, so it measures the conductivity of the column effluent. So this liquid coming out of the column. And then it's recorded most often in the computer. So in principle, it's the same as with every analytical chromatography, just this suppressor is different. So why suppressor? The problem is that that those acids or bases that are used in eluent, they cause high conductivity of eluent itself. And now if we have a small amount of analyte ions present, then this changes this conductivity only slightly. So the conductivity of eluent itself is very high, and analyte adds just a bit to this conductivity, so it conducts only a bit better. So this is difficult to measure. We can imagine that if we want to measure, let's say, thickness of this paper, then we can use this measuring device. I don't know its name in English, to measure the thickness of paper like this. Easy, right? Do you know its name in English? Right? Caliper, yes. Okay, so easy to measure. But if I put it on the table and want to measure its thickness together with the table, we don't have caliper of this size. So we have to measure the distance, big distance, and then with paper and without paper, and from this difference calculate the thickness of paper. Very inaccurate. So the same with high conductivity of eluent and analyte ions in there. So if we could somehow get rid of ions in the eluent, then we could measure the thickness of paper directly, right? Can we use eluent just water without using any acid or base in it? Maybe in some very special cases. In most cases, we still need control over pH. And therefore, without any acid or base, just pure water, this wouldn't work. So then we have to get rid of the ions after the column. So the ion exchange process takes place inside the analytical column. So we have to eliminate the ions of acid or base after the analytical column. And here is one example. The buffer solution is hydrochloric acid, millimolar. Then sample is just alkali metals, just as an example. For analytical purposes, we use a cation exchange column. Of course, as we are interested in alkali metals, then cation exchange column is needed. And now the suppressor column is anion exchange column. So cation exchange column does its work. It separates the alkali metal ions into peaks. And now when the flow enters the suppressor column, then suppressor is anion exchange. So on the surface of anion exchange, it's initially in hydroxyl form. So hydroxyl form, so OH minus groups are attached to the surface of this column. And as the eluent contains chloride ions, chloride anions, then chloride ions displace OH ions. Those get into the eluent, and chloride remains there. Okay, now we have in the eluent hydrogen ions from the hydrochloric acid, and then we have we displaced chloride ions to hydroxides. So it means we have even worse situation, isn't it? Because both hydrogen ion and hydroxide ion both are highly conductive. Yes, they react to form water. Sorry?
So it becomes neutral and then it wants to build the process.
Exactly. So, yes. So we capture the chloride ions, replace them with hydroxide ions. Hydroxide reacts with hydrogens. Water is formed, and the resulting solution contains just alkali metal ions. And we can measure the conductivity because of alkali metal ions without any interference from the acid cations or anions. And this is what the conductivity cell does. Okay, the slide also says that the cation exchanger, this analytical column, has low capacity, and the suppressor is of high capacity. Well, capacity means that the amount of anions it can exchange. It's quite clear that the more we can exchange with this column, the better. So this is fine. Why this should be of low capacity? Because we don't want to spend too much material on this column. So I mean the sample material. So it's quite common that those analytical columns are of low capacity. Yes?
In case of suppressor, if the column is anionic exchange, it will be cationic exchange?
Yes, yes. If the analytical column is cation exchanger, then this is anion exchanger. And if analytical column would be anion exchanger, then this would be cation exchanger. Indeed. If we need to use the suppressor column again, we have to regenerate it. And in case of this anion exchange column, it's regenerated using bases, so hydroxides. This is a problem. We need to regenerate the column quite often, the suppressor column. But luckily, membrane suppressor columns are in use, which are not as good as the usual types, as efficient as the ones, but still work, and they don't need regeneration. They are regenerated constantly. And those suppressor columns, membrane suppressors. Over here, the analyte or the solution from the column, the effluent, enters from the top into this central stream. So in this case, it contains sodium cations and then some anions. And these anions X, those are our analyte. So, and as usual with the case of anions, some hydroxide containing eluent is used. So sodium hydroxide in this case. As they pass down the central stream, then the electric field is applied between anode and cathode. Cations from the eluent, so sodium ions, they start moving towards cathode and penetrate the cation exchange membrane. So sodium ions are eliminated into this compartment now. And from here, the stream of water just carries the sodium ions away. Okay. No objections. So, as I explained so far, this liquid in this central channel will be negatively charged, right? We can collect negatively charged liquid from there. Because sodium ions moved to the right-hand compartment and were carried away. And we just have the negatively charged liquid here. Yes, I didn't mention that hydrogen has to reach this central channel and this equilibrates this negative charge. So, of course, this hydrogen also reacts with hydroxide ions. Again, water is formed. And now we have the situation as in previous slide that the highly conducting hydroxide ions are reacted with hydrogen to form water. And in the output stream, we have just the analyte. This X is the analyte, and this is the only thing that we measure the conductivity for. Method development in ion exchange chromatography. Well, strong anion exchange is used for acidic and anionic compounds, strong cation exchange for basic and cationic compounds. Eluents, water-based buffers, so pH usually higher than 6 for strong anion exchange columns and analysis, and lower than 6 for strong cation. If analyte pKa is known, then pH should be higher than pKa value for anion exchange and reverse for cation exchange. Concentrations, tens of millimolar concentrations. Now, we may add also some additives. So we may add the eluent component B or other eluent component which contains also the same buffer, but additionally some salt. And the purpose of this salt is to provide the counter ion which helps the analyte ions to elute from the column. If analyte does not elute from the column, then we can try higher temperature or addition of organic modifier. And if still not successful, then we can switch to another column. If we then achieve the retention, satisfactory retention, so the retention factor between, let's say, 0.5 and 20, then selectivity is modified by using salts or pH or organic additives. Applications of ion chromatography, mostly anions, are analyzed just from the world of cations. The big part of those are metal cations, and for this atomic spectroscopic methods are used. So this would be a big field for ion chromatographic analysis, but this is taken over by spectroscopic methods. So mostly anions. Amino acids, peptides, proteins, some nucleic acids. So indeed, part of them can be also analyzed using reverse phase chromatography, but occasionally then ion exchange is used. Any questions regarding ion exchange chromatography? Exhausted. Not only questions, but you seem tired also. So. Okay, so to make you even more tired, then let's take an exercise in between. So the exercise, I will share the screen. And I will give you some paper, so you write it on the paper. So here it goes. There are two chromatograms. Some people are smiling, they know those chromatograms, but never mind. So this first peak corresponds to this compound, parabens, so methylparaben, ethylparaben, propylparaben, butylparaben. So the peaks are shown and their corresponding compounds. The order of the peaks is the same and correspond to the same compounds. So your task is to guess something, not guess, educated guess. So to write something about those chromatograms, what you see here, and also what you think is the change that has been made in between those two chromatograms. So why this one has shorter retention times than this one. Try to guess what is the type of chromatography. Try to be quite specific. Then briefly describe why those compounds elute in this order as they elute. Use words retention time and also pay attention to peak width and peak symmetry. That's it. Many questions already. So I will give you some paper. And right. Enough? One more. And I thought you enjoyed the cinema. No, yeah. Better now. Okay, online participants, the task is the same for you. So describe those two chromatograms and what you see there. Make a guesses, describe retention time, and why retention time is shorter on the second chromatogram. And maybe it's easier if we number the peaks 1, 2, 3, 4, and chromatograms also, first and second. And I will do this. So let's number this like this. So this is chromatogram number 2. And compound and peak number 1 is here. Number 2. Number 4. Now here the peaks have the same numbers. Ready? Please try to plan your writing so that in 2 minutes you bring your paper. 2 minutes. Seconds. Okay, please write your name on the paper and please, everybody personally, please bring and put the paper here. Come from this side and then proceed that side back to your sled. Just so that you can get some exercise. Thank you. And this side. Now from here, and you proceed that way. Even longer. Here is the way. So. Yes, now please bring it. Exactly. Okay, online participants, just a comment for you that we have some exercise here so that people don't look so that tired anymore. Okay, thank you. And this was just a little practice to speak about chromatography or to write about it. Okay, we still have a couple of chromatography types to go. So let's try to go and see how far we reach. So next one is size exclusion chromatography. Do you know about this? No? No? Yes? No? Not much, seems so. Okay, in size exclusion chromatography, the separation is based on the size of the molecule, and this should be the only characteristic. So all those chemical interactions should be excluded. So that's quite different from other chromatographic types. So only the size. There are two modes. One is called gel filtration, which uses water-based eluents and often used in protein separation. And the other subtype is gel permeation chromatography, uses organic solvents and very often used for synthetic polymer separation. Separation principles and the chromatography type is still the same, size exclusion chromatography. So depending on the size of molecules, they either enter the pores of the stationary phase or do not enter the pores or partly enter the pores or pass the pores. So if the molecule is large, then it's so big that it cannot enter any of the pores and elutes the column first. If the molecules are very small, then they can go through all the pores in the stationary phase, and therefore they elute the latest and not well separated. Now, the average sized molecules, those can enter only those pores where they fit in. They cannot pass all the pores because some of the pores are too small, and to those too small pores they just do not pass. And therefore those average or middle-sized molecules, the time they spend passing those pores depends on into how much or how long pores they fit in. So the smaller is the molecule, the more pores it can pass, therefore the longer is the retention time. But once again, it's important that the stationary phase itself does not or shall not interact with analytes. So there should be no interaction with analytes. It's difficult to draw it schematically, but well, let's use this image then. Large molecules are so big that they do not enter into any pores, and therefore their retention time is very short. Very small ones, those yellow dots, those enter all the pores, go through the smallest pores, so their retention time is long. And middle-sized, the orange ones here, those pass some pores, but do not fit into others. Therefore, their retention time is average. And of course, if there are different of those orange type molecules, then they pass or can enter into different pores. And stationary phases, in case of gel filtration, it's very often dextran or polyacrylamide. Perhaps this polyacrylamide is the most well known. In gel permeation chromatography, again, this polystyrene divinyl benzene columns are used, extensively cross-linked, and this controls the pore size. What can we do with size exclusion chromatography? The separation is based on the hydrodynamic volume of compounds. which is the volume of molecule and its surrounding molecules. And it allows separation based on chain length or the geometrical structure where exactly specific groups are situated. Then according to functional groups, for example, how many polar groups it has and how far they are from each other. And structure can be more linear or more branched, and if the molecular masses are the same, then we still can differentiate them by their size. So yes, once again to stress, this is not exactly equivalent to the molecular mass. So molecules of the same molecular mass may have different shapes and therefore different size, and then they are eluting as different peaks. It's quite often assumed that it's directly related to molecular mass, but this is not true. What kind of information we obtain? The retention time gives us the molecular weight, more or less, if we make some assumption about the shape of the molecule. Then the chromatographic peak shape tells us about the molecular weight distribution, so smaller or bigger molecules. And calibration is always necessary. We need to calibrate the size of molecules, and it's very important that the calibration substances have as similar as possible to the analytes. The structure is as similar as possible. And of course, the sample and the calibration mixture, they have to be dissolved in the same solvent, so that otherwise the conditions have to be identical. Here I have one example of analysis of synthetic polymer. Columns, in this case it's plural, because 3 columns were connected in a row. To separate different molecules of different sizes, then 3 different columns were connected. And first of them had 4 sizes in the order of magnitude of 50 angstroms, then 100 angstroms, and then 1000 angstroms. So 3 different columns attached in a row, altogether 90 centimeters of column. Quite impressive. Eluent was THF, tetrahydrofurane, 1 milliliter per minute. System had 2 detectors, and for calibration, polystyrene was used. And information about this polystyrene standard is given in the table. So molar mass of polystyrene fraction with molecular mass of 66,000. This eluted in a in elution volume of 18.25 milliliters. And let's say the fraction with molecular mass 2,280 eluted at 23 milliliters. So we see that indeed bigger molecular masses elute earlier, and the smaller is the molecular mass, the bigger is the elution volume, or we can relate it to the retention time. And the calibration elugram. What an interesting name for this, right? So on the horizontal axis, we've got elution volume. As the flow rate was 1 milliliter per minute, then the numbers for minutes would be the same. And the molar mass is on the vertical axis. And note that this is a logarithmic scale. And we have, well, not quite linear relationship, but not too far from linear. And this is about the calibration. So calibration value. Now, for sample, the detector response is shown on the axis and dilution volume on the horizontal axis. And we see that the peaks are present, not well separated, but still we have peaks. So earlier in the chromatogram, we have higher molecular masses and later smaller molecular masses, right? So this is the, let's say, raw data. Now we can convert it to a bit more useful data by converting the horizontal axis to molar mass, because this elution volume is related to the molar mass, so it's converted to molar mass, and now the peaks are reversed. We see that the smallest molar mass, the small peak here on the previous slide, it was at the far right, because this is the low molecular mass, passes all the pores, and low molecular mass appears here, and bigger molecular mass is then to the right. Okay, so this was this synthetic sample and example of how it looked like. There are a couple of examples more, but our time is over. So questions so far?
We don't use any like solving for we use the alien for that.
Well, the solvent should be such as to avoid any interaction of analyte with the stationary phase. So THF is so good solvent that it doesn't let any of the polymer molecule to interact with the stationary phase. So that's why it's very good solvents are used.
But we can't do any like gradients. So that if we have like two peaks are like close together, so we just
usually gradients are not done because there is no interaction between the molecule and the stationary phase. Therefore, via eluent, we must not be able to change anything. So every solvent that we use has to guarantee that there is no interaction between the molecule and the stationary phase. So yeah, theoretically, of course, we can alter the eluent composition, but this is not meant for size exclusion chromatography. Okay. Very good. And then we are done. And thank you. And by the way, next Monday there is no lecture, right? So there will be homework. I will send them in Moodle. Okay. Thank you, and then see you next Wednesday.